Hello everyone, I'm Zeki and I'm going to present our work titled A Proposal for Networks Capable of Continual Learning. As it is well known, existing methods of machine learning are prone to catastrophic forgetting, that is, the loss of existing knowledge when they know something new. And in this work, we want to propose an alternative learning methodology, which, as we showed in our paper, is inherently capable of learning continually throughout the preservation of the past responses of individual computational units. In this presentation, I'm just going to give a brief overview of the learning methodology and the core principles of adaptation. The full details can be found in our paper. So in our method, which we call modellian, we use a principle of local component level variation and selection. Initially, when there's an event to be predicted, the system constructs a new computational unit, which hypothesizes the requirement for the presence of each of the alternative sources of explanation for that event that are observed in this given time instant. And then, based on further observations, these alternative hypotheses that have been hypothesized to be required for the prediction of the event are gradually refined to a subset that is absolutely necessary for the prediction of that event. This process is repeated for negative conditionings as well as alternative upstream conditionings in order to be able to represent functions of arbitrary complexity in a logical manner. To give an illustrative example, suppose that the event you want to predict is the running of a prey animal. Let's say that in the first observation, you see a prey animal running in the presence of a predator and in a rainy environment. Then you hypothesize the presence of the predator and the rainy environment both being required for the prey animal to start running. After that, you may observe the presence of a rainy environment in which the prey animal does not run. In that case, you refine the presence of the rainy environment as an explanation that is required for the event that you want to predict, so that you are left with the presence of the predator for the prediction of the running of the prey animal. In an even further observation, you may see that the prey animal doesn't run from a predator if it has some sort of protection with itself. In that case, you condition the presence of a protection to be a negative conditioner for the event that the prey animal starts running. Depending on your even further observations, you may form further upstream conditions and represent complex ways, complex cases in which the prey animal starts running or not. Of course, the learning methodology that we just described is only applicable to simple state variable lists. We also present an extension of this learning approach, which we call model-land with network refinement, or MNR for short, in order to operate to observation spaces that can be represented as networks, such as complex visual spaces. This learning approach is identical to the previous one, except that instead of direct refinement of individual state variables, we construct a refined network that is a refined form of multiple networks that have been observed before, in a way that preserves only the paths that are present in each of these networks as edges in the final refined network. In the example that you are seeing on the screen, this corresponds to path A to D, path A to C, and path Z to C, which are present on both of the networks that have been observed before. We validate our learning approach in two different experimental regimes. First, we validate the success of Bayes environmental modeling framework on a simple finite state machine environment. Here, the aim of the agent is to learn a correct environment model and then use them in a simple planning algorithm to choose good actions that can reach to the goal at a short time. And then we validate the design of MNR on MNIST in a way that we want to test continual learning via the exposure to samples in an ongoing manner instead of being exposed to them as a batch. For the second set of experiments, we use a simple feature representation that is based on shape information to convert MNIST images into networks. This feature representation is not fully expressive, and hence our method cannot learn with a perfect accuracy that is seen in neural networks. However, right now it is adequate to show the pattern of progression of learning in a way that is continual and does not have any forgetting. In our results with basic environment dynamics modeling, we see that the agent learns a good model of the environment as apparent from the number of steps that are needed to reach the goal. And we also see that if the agent is exposed to different environment subtypes, its performance on a previously observed environment subtype does not decay, and hence shows that the learning takes place continually without any catastrophic forgetting. We see a similar results in our test with MNR, where exposure to new classes does not result in a huge decay in the performance of a previously observed class. This contrasts sharply with what happens in cases like neural networks. For example, in a fully connected neural network, the agent at initial cycles of exposure loses completely all the performance that it has obtained in a previous class that was observed. The performance can only gradually recover, and that is only to a partial degree after repeated exposures to same class sets in a cyclic manner, which makes the problem basically equivalent to a batch learning with a slow time scale. And in case of a convolutional neural network, we see that the agent cannot recover performance at all, showing complete catastrophic forgetting. In contrast to both of these cases, our approach learns continually and does not forget the information, even starting from the first cycles of exposure. To conclude, we presented the early design of a learning framework that is inherently capable of learning continually. We foresee extensions of this methodology to more expressive feature representations to be able to reach the perfect accuracies, as well as subsequent application to higher complexity problems. Thank you.